Thermal management of electronic products and the application of thermal conductive polymer. Thermal conductive polymer, also known as TCP, has become an important part of the thermal management solution. In thermal management design, there are two types of cooling processes: active cooling and passive cooling. Active cooling requires extra equipment and energy to power the equipment. It generally leads to more complex and expensive designs than passive cooling. Passive cooling systems, on the other hand, rely solely on the material's thermodynamics to perform the heat transfer process. This method is more commonly used and has the advantages of being the least expensive and the easiest to implement. Recently, TCP has evolved and is becoming a vital part of the passive cooling solution. Now, we are going to introduce the characteristics and the application of TCP. The three fundamental methods of heat transfer are conduction, convection, and radiation. One of the key factors affecting the effectiveness of thermal management is the material's thermal conductivity. Plastic materials have been extensively applied on housing and the structural components of electronic products. Usually, the engineers would have to adopt active cooling solutions with extra components to meet certain thermal management requirements. This leads to more complex designs. But thermal conductive polymer with thermal conductivity of 5 to 25 times higher than traditional plastics can help to simplify the design and reduce the cost. This makes it a better alternative to traditional plastics when heat dissipation is required. The effect of high thermal conductivity material has been applied in the system. We have decided to do a thermal simulation model in order to find out if materials with higher conductivity have any positive effect on thermal management. The design of the thermal simulation model looks just like the picture shown in the top left corner. We place a heat source in the middle of the sheet and then take one temperature reading from the middle point directly under the heat source and one from the edge of the sheet. We maintain all test conditions the same, with the only variable being the materials that are used to make the sheets. The first test sample is a plastic sheet made out of traditional plastic with thermal conductivity of 0.2 and heat emissivity of 0.9. The second test sample is a plastic sheet made out of thermal conductive polymer with thermal conductivity of 5.5 and heat emissivity of 0.9. The last test sample is a metal sheet made out of aluminum with thermal conductivity of 180 and heat emissivity measured at 0.3. From the test results, we discovered that when compared with traditional plastic, thermal conductive polymer greatly reduced the temperature from the heat source by about 80 degrees Celsius, and the spread of heat is much more even throughout the sheet. On the other hand, aluminum with the best thermal conductivity in the group was only able to reduce the temperature by 8 degrees, as it has a much lower heat emissivity. Comparing the results from these three test samples, we can conclude that when TCP is being applied to replace traditional plastics, the temperature drop is obvious. The heat is distributed more evenly. From both a theoretical standpoint and the supporting evidence from the simulation results, we confirmed that thermal management is greatly improved when TCP is being applied. But aren't you curious what the real performance would be like if TCP were applied on actual electronic products? Here, we are going to conduct an experimental study on a wireless charger set to find out. The wireless charger set used in the experiment includes a wireless transmitter, wireless receiver, and a smartphone. The experiment is to observe the working temperature of the transmitter. The transmitter consists of a back cover, printed circuit board, coil, and front cover. The front cover will be replaced by TCP, and the results will be compared to the original cover made out of traditional plastics. Two sets of experiments will be conducted. Experiment number 1. To observe the change of surface temperature on the front cover. Duration of the experiment: 1 hour of charging time. In this experiment, we use a thermal imager to observe the change of surface temperature during 1 hour of wireless charging. The result of our first experiment is presented by two images captured on the thermal imager. First, let's look at the image on the left, where traditional plastic is used to make the front cover. In the highlighted area, it distinctly shows that the distribution of surface temperature is uneven. Heat is mostly centralized, which is the cause for the transmitter to be so hot, with a measured max temperature of 45.7 degrees Celsius. Now, let's look at the image on the right, where TCP is used to make the front cover. In the highlighted area, the heat dissipation improvements are obvious. Heat is distributed much more evenly and is no longer centralized. The measured max temperature is only 35.8 degrees Celsius. From the results of the experiment, we can conclude that TCP can help reduce the working temperature on the surface by around 10 degrees. Experiment number 2. To measure the change of working temperatures on the key components of the transmitter. Duration of the experiment: 1 hour of charging time. In this experiment, we pick 4 key components on the circuit board that are most likely to become the heat source. We then connect the surface of those 4 components with K-type thermocouple wire to our data logger to record the temperature changes during operation. The 4 measuring points are T1, T2, T3, and T4, as shown in the image. We have gathered 2 sets of measurements from this experiment. The first set of measurements are the ones with a front cover made out of traditional plastics. The second set of measurements are the ones with a front cover made out of TCP. When comparing these 2 sets of results, we can conclude that when TCP is applied, the working temperature of those 4 components can be reduced by 4 to 7 degrees. Based on our research and the experiments conducted above, we can conclude the following. From both a theoretical standpoint and the supporting results from the simulation, TCP has proven to be an effective way of dissipating heat from the heat source due to its higher conductivity value when compared with traditional plastics. The results from our wireless charging experiment showed that when TCP is applied, not only does it help lower the temperature of the front cover and the key components, the temperature is also spread more evenly. From the test results, it could be concluded that many benefits could be obtained by applying TCP to a product's thermal management solution. TCP could effectively reduce the temperature from the heat source, which in turn prolongs the product lifespan. Thank you.